Hello everyone, I am Radha Kumari Pani, Assistant Professor in the Department of Metallurgical Engineering at Vedang Institute of Technology. So, in former classes, we have discussed about the important topics in chapter of phase transformation in metallurgy. Okay. So, in last classes, what we have discussed, I would like to summarize in few minutes. So, first solidification, why this is solidification process is important in phase transformation process, and what is the prospects behind this solidification process. Okay, generally if you are talking about the solidification, one thing comes to mind that something like liquid metal comes to solid phase. This is the phase transformation from liquid phase to solid phase. So why this solidification process happens and at what parameters? Okay, if you are decreasing temperature, then we know that by decreasing temperature the force of attraction between the atoms and atoms, that will going to decrease. Okay, so sorry, that will going to increase, because if you are decreasing some temperature, then you are decreasing kinetic energy. Also we know that kinetic energy is half mv square. That means velocity also decrease. Then the atoms will not go to moving haphazardly or randomly motion, so that the atoms comes close to each other, so that the solidifies, it starts to solidifies. That is known as solidification process. Okay, just this is the reciprocal of what melting. How we are how we are converting solid phase to liquid metal by giving some high temperature, by applying some force. Okay, by giving high temperature, its kinetic energy will increase. Then the solid metals comes to liquid. This at some definite temperature, that is known as melting point or Tm. Like that, solidification is reciprocal to that. Also in former classes we have derived one approximation, that is Turnbull's approximation, and what is that formula is del G is known as L del T by Tm. Okay, so on basing this equation also we have discussed 3 to 4 I think questions. Okay, what is del G? That is change in gives free energy, L is latent heat of fusion, and del T is changing in temperature. This is T, capital T, and Tm is melting point. Okay, now in today's classes we'll discuss about what that is the solidification of pure metal. Remember, in case of pure metal, solidification happens at some definite temperature. Okay, now I have told that by suppressing the temperature, or we can say by cooling, under cooling process solidification happens, because the kinetic energy will go to suppress. One thing remember, at freezing point, the liquid phase and the solid phase of pure metals, their kinetic energy will be same. Here in this line, the kinetic energy of the atoms in the liquid and solid phase must be same, but there is difference in the potential energy, and that difference potential energy is known as latent heat of fusion. We are this latent heat of fusion, or in the mathematical we are del HF. Okay, so this graph is the solidification of pure metal cooling curve, and y-axis temperature parameter and n-axis is time parameter. If you are suppressing the temperature at this point, this is known as the pouring temperature. That means the temperature at which the liquid metal is poured to some chilled zone or mold wall, we can say, that is known as pouring temperature. As we are decreasing temperature, the liquid metal start to solidify. Okay, at this point the freezing process begins. Okay, at this temperature and at this time, freezing happens. Okay, and at some constant, it goes on constant temperature, the freezing continues, and at this point freezing completed. Freezing completed. Okay, so this is from this to this is known as solidification. This time is known as solidification time, total solidification time, TST, total solidification time. And this curve, this as we can say, this is the sharp decrease. At some sharp temperature, this starts to freezes. Okay, so that we can say the pure metal, the solidifies happens at definite at constant temperature, but in case of alloy, we'll see in the other slide, in case of alloy, this is happen in a wide range of temperature or long range of temperature. Okay. So subsequent release of heat of fusion raise the temperature to the freezing point, as we are decreasing the temperature of the liquid metals, so that the concept behind it, the moving the kinetic energy will be suppressed, the force of attraction will be less, more, so that the atoms comes to each other and they start to solidify. And maybe this is the undercooling. Okay, this is undercooling required may be reduced by the presence of solid impurity. This can be enhanced by the presence of some solid remember, there is always some grain boundary, always some impurity is there in the liquid. Okay, so that that enhance our solidification process, by which the amount of surface energy, this is surface energy required. Okay, so in the next slide, it's talk about the concept. When the temperature of the liquid metal dropped sufficiently at the freezing point, the stable aggregate or nuclei appear spontaneously. In metallurgical perspective, if we are talking about the solidification, remember, first stable nuclei is formed. That means, suppose this is the one mold wall, okay, in where we are going to solidify the liquid metal. What happens at some temperature, this is the liquid form. Okay, at some temperature, the stable nuclei start to form. As we are going the undercooling process, suppress the temperature, more nuclei will be aggregate to form. This is called the growth of crystallization. Okay, first stable nuclei, then crystallization growth, so that at last we are getting the perfectly the solidification of metal, that is the metal will be solidified. Okay, so this is what it written here in the slide. At cooling continues, more atoms tend to freeze and they attach themselves already existing nuclei. Already one stable nuclei is formed. As we are suppressing the undercooling process, more nuclei will attach to that stable nuclei, so that nucleation growth will be happen, and to form is a space lattice. That the nuclei formation will be happen, remember, in 3D dimensional. That is known as space lattice. We know that what is the space lattice? Space lattice is nothing but it is the crystallization growth in the lattice point in 3D dimensional, that is in x, y, z axis. So each nucleus is formed by the chance. So the crystal exists as pointed at some random dendrite. What is dendrite? Remember, if the liquid metal starts to solidify at some point, okay, tree-like structure will be formed. At some process, this tree-like structure will be formed, and this is known as the dendrites. Okay. So what happens in the different directional, okay, there is no some specific directional, in the different 3D directional dendrites will be formed, and growth of the dendrite will be disturbed, will be obstructed by its neighbor. So we'll get the different external shape of the solids. We'll not get the what we are imagine. I would like to get some this type of shape, but no. Actually, what happens, because the crystallization occurs at different direction and different crystal axis will go there. So we are getting the different external shape of the solids, and these crystal are found in the commercial metal known as the grain. Okay, and because of the variation in the external shape, the area along which the crystal met known as the grain boundary, means this portion. Okay, if we are taking about this dendrites, and the outside is known as the grain boundary. So in the next slide, we'll better understand, okay, what I am talking about. So first, and this is the liquid to solid phase transformation, that is solidification. Okay, so first this is the liquid like this. First what happens, in the some solid or stable nuclei will form. Then here, as we are talking about the tree-like structure, okay, the growth of the crystal will happen, so that when the two crystal going to join, the boundary at the boundary, okay, is known as grain boundary. Here one tree like structure is crystal is shown, and here another crystal. So the boundary between this, okay, here and the boundary between those two crystals is known as the grain boundary. So now the crystallization growth has happened. At last we'll get this solidification, complete solidified metal. Okay. So due to the mismatch orientation or mismatch three-dimensional formation of solids, we'll get non-crystalline or amorphous metal. Okay, structure. So what happens? This is the liquid. Okay, this is what I have said in the earlier slide. This, if you are taking some mold wall, if you are pouring some liquid metals, what happens? At that time only the liquid surface, at the surface of the mold, the liquid metal starts to form the thin surface of pure metal. Okay, this is known as the chilling zone. Okay, this surface. At the time when we are pouring some liquid metal to a mold wall, at the surface of the mold wall, the tiny thin surface of the metal will grow. Okay, this is chilling zone, and at the center where this is elongated, these are known as the elevated or elongated, okay, grains is known as the columnar grains. Okay, these all are elongated. This will form towards the center. Okay, this is known as the columnar grain. And at the center, this is equispaced grain. That means at the center the stable nuclei will form. Okay, and towards the center the columnar grains will be formed, and the tiny and thin little grains will be formed at the surface of the mold wall. Okay, this is known as the casting of a pure metal. Normally the casting of pure metal means the three types of grain we'll see at the surface, towards the center, and in the center. At the surface, the thin tiny liquid metals will start to form the solid metals, and at the towards the center, that is elongated columnar grains will be formed, and towards the in the center the equispaced grain will be formed. So as you can see, the most of the alloy freeze, I have already told about, the most of the alloy freeze over the wide range of temperature. Okay, so this is the phase diagram of copper and nickel alloy system. How this solidification is going out in the alloy system, we will understand in this slide. So this is the pure nickel. Okay, this is pure copper, and this is the temperature of pure nickel, 1455 degrees Celsius, and the temperature of the copper is 1083 degrees Celsius. As we are going decrease the temperature with, and the x-axis the composition of copper will increase. Okay, so what happens, as we are decreasing the temperature, the nickel and copper alloy will mix together and they will form the liquid solution. This curve and this curve, this at the bottom to this blue line is known as the solid solution. Solid solution means solid nickel and solid copper plus liquid metal. Okay, solid solution means some composition of nickel will be there, solid nickel, and some composition of copper will be there, and the liquid mixture of two alloys. Okay, and at the above of the red line is known as the liquid solution or liquidious. Liquid solution means it is the liquid mixture of the two alloy, nickel and copper, and between these two line, liquid plus solid. Okay, as we are going the decrease the temperature with the composition of copper, we'll see this type of graph in the alloy. Not this is, as you can see, this is quite different in the pure metal. In pure metal, what happens? There will be a sharp decrease in the temperature when the freezing starts to begin. Okay, and there will be maintained some constant, not constant, some phase of range, some decrease of range. This is the temperature and the time. Okay, this is the temperature time curve for alloy, and last slide we have seen the temperature and time curve for pure metal. In case of pure metal, what happens? There will be sharp, not curve, sharp. Okay, so sharp decrease and the constant temperature range. Okay, from freezing starts to begin and where the freezing starts to end. But in this case, we can see there will be small incline, downward incline. So this is the phase of temperature. Okay, this is the solidification. This is the solidification of alloy system. This graph. Okay, where the temperature, the solidification process happens at some this range of temperature. But in case of pure metal, there will be no range. The sharp decrease in the temperature. Okay, so as we have in the last slide, as I have told, this columnar grains and equispace, here it is written, as you can see, this is the chilled, this is the mold wall, and the surface is known as the chilled zone. Okay, and the center, at the center, as we can see, the stable growth of nuclei, and this is the equexed zone. At the center, this is equexed zone, and towards the center, the elongated grains is known as the columnar zone or columnar grain. Okay. So, cast structure, the casting structure of a metal. What is the casting structure? Normally, the casting structure belongs to three zones: chilled zone, columnar zone, and equexed zone. As already I have told, what is chilled zone? The region of small and randomly oriented grains that form at the surface of the casting. Okay, at the mold, if you are pouring some liquid metals, at that time, what happens? The chilled grains will be formed at the chilled zone, means at the surface of the metal. This is the tiny little grain. Then the columnar zone, the region of at the preferred orientation that forms as a result of competitive growth during the solidification of casting, because there will be competition between the metals. Okay, so there will not some definite orientation, there will be some mismatch of orientation. Some will form at the surface, some will form towards the center, and some will form in the center. So the due to the rapid result of competitive orientation, the columnar grains are formed. Then equexed zone means this is formed at the center of casting. This is okay. This is known as the equexed zone, and this is the total scenario of the casting structure of a pure metal. Now, solidification belongs to two processes. First one is nucleation, second one is growth of stable nuclei. Okay, first at some space, some stable nuclei form. What happens? We go some decreasing the temperature or some undercooling process, growth of stable nuclei which starts to form. So nucleation, as we know, there is two types of nucleation. Remember, one is homogeneous nucleation and another one is heterogeneous nucleation. What is the difference between this homogeneous and heterogeneous nucleation? Remember, in the homogeneous nucleation, what happens? The nucleations happen spontaneously throughout the parent phase. Okay, what is the parent? The liquid parent phase. Throughout the parent phase, spontaneously happens to nucleation starts to form. That is known as the homogeneous nucleation. But different to that, heterogeneous nucleation means the nucleation happens at some preferential sites. That means some grain boundary, or it can some impurities. Okay, at some dislocation, the nucleation starts to form. That is known as a heterogeneous, but homogeneous, constantly spreading over the parent phase. And this is some different types of nucleation. Okay, this is given first, the gas creation of liquid droplets in the saturated vapor. This is also the nucleation. And the liquid formation gaseous bubbles, that means in the liquid water, the ice starts to form. That is also one example of nucleation. And solid liquefaction of crystal, as we have seen in the earlier classes, the amorphous or non-crystalline solids starts to form. Okay. So this is the difference between homogeneous and heterogeneous nucleation. As I have already said that the probability homogeneous equation are throughout the parent phase is same throughout the parent phase is homogeneous, but drastically change to that heterogeneous. What in heterogeneous equation, this will happen some preferential sites like some dislocation, some grain boundary, or some inclusions happens. Okay, liquid to solid in the case of solid to solid. So today's class up to this much. In the later classes, we'll briefly discuss about the homogeneous nucleation. Okay, and also what is the three parameters will have what happen. Three parameters will happen the homogeneous and heterogeneous equation. That is reduction names, Gibbs free energy, and interfacial energy and strain energy. Will briefly discuss in the later classes. Thank you so much.